it's my great pleasure to introduce Jean-Éric Pin from Université Paris, Denis Diderot. His title is, as you can see, a non-commutative extension of Mahler's interpolation theorem. Jean-Éric, please.
Thank you very much. First of all, thank you very much for inviting me to this seminar. I have to say this is not that much geometric, but as far as non-commutativity is concerned, you can it would be difficult to be more non-commutative than this lecture. So this is a joint work with Christoph Reutenauer, who is supposed to assist me just if I said something wrong. And it's also based on earlier results with Pedro Silva from the University of Porto in Portugal. Okay, so I have to find. This is this. Okay, so here is the topic, the original topic. So let me state a short version of the original Mahler's interpolation theorem. I will elaborate on this in the next slide. So for now, this simple statement is the following. You start with a prime number p, and you consider a function from n to z. And this function is uniformly continuous for the p-adic metric if and only if it can be uniformly approximated by polynomial functions. So let me explain this in more detail and give a more precise statement of this Mahler's theorem. So for this, I need to introduce a few definitions. So I will introduce first the difference operator. Then an important part is the Newton's forward difference formula. And another one is Newton bijection. And then I will be able to state the original Mahler theorem. So the difference operator is a very simple thing. You start, as I said before, with a function from n to z. And the function delta f is simply defined let me use this. So by delta f of n is the f of n plus 1 minus f of n. And you can iterate this difference operator, of course. So if you do this twice, you get this formula. And if you did k times, you get this formula involving the binomial coefficient with some sign, alternating sign. So you get this formula. And by convention, the zero iteration is just the original function of n. So let me give you some examples. If you start with the function r to the n, then the first difference is difference operator gives you this, r to the n r minus 1. If you iterate twice, you get r to the n r minus 1 squared, and k times r to the n r minus 1 k to the k. If you consider the parity function, which is 0 if n is even and 1 otherwise, and if you make a small computation, we show you that this is essentially to the power k minus 1 with a sign which depends on k. And this is depends on parity of n, sorry. Okay, so what can I do with this? Here is this Newton's forward difference formula, which is a nice combinatorial property, which holds for any function from n to z. This formula tells you that then there exists a unique family delta k of integers, such that you have this formula. F of n is the sum of the binomial nk multiplied by this coefficient delta k. And it turns out that this family delta k is given by this. You take the k time iterated difference operator applied to f at 0. And of course, this sum is apparently infinite, but in fact it is finite because the binomial coefficient vanishes for k larger than n. So this is one of the combinatorial ingredients that we will need later on. So let me come back to my example. If you start with my function r to the n, and then you remember that delta k of f was r to the n r minus 1 of k, so taking this at 0, you get this lowercase delta k is this quantity, and therefore you get this equality. And the same way, if you start with the parity function, you get this equality, where you see the coefficients this time are power of minus 2. Okay. So I'll give you some further examples just as exercises. I don't intend to detail this that much, but speaking of combinatorics, of course, you know, you have to talk about the Fibonacci sequence at some point. So here it is. If you start with the Fibonacci sequence, it turns out that the delta k of f are themselves Fibonacci numbers up to a sign, and you get this formula, f of n over there, this one. And another nice combinatorial fact is that if you start with a factorial function, the coefficient you get here, the dk, should be delta k, but I use dk, and there are the number of derangements. That is a permutation of k elements with no fixed point. And again, this is an exercise if you want to make it in combinatorics. So another interesting fact is that this map, which maps f onto the family of coefficient delta k of f, is actually a bijection. So you start with, if you have this decomposition, this sum, f of n equals this sum, then you can recover the delta k of f with this formula. So for instance, if you have the parity functions on the left-hand side, you get the powers of minus 2 on the right-hand side. If you start with Rn, you get this R to the minus 1 to the power k. And for Fibonacci, you get also this. And all these things are things we have to extend in the non-commutative case later on. So just as you have seen, there was a little bit of topology in this theorem. So just to remind you the p-adic metric. If you have an integer r, you look, let's consider, you look at the largest exponent of p in the prime factorization of r. And this gives you, the p-adic norm is just this quantity, p to the minus n. And the p-adic distance between two integers is just the distance dp of rs, which is this. So let's briefly look at an example. If you start with 512 and 12, the difference is 500, which is 2 to the 2, 5 to the 3. So therefore, the two-adic distance between r and s is 2 to the minus 2. The 5-adic distance is 5 to the minus 3, corresponding to this 3 over there. And otherwise, it's p to the power 0 for all the prime numbers. So, and now here is the full statement of Mahler's interpolation theorem. If you start, you remember, we start with this function f of n, which can be decomposed as this sum of binomial nk delta k of f. And then you consider the truncated series up to r. So you define a polynomial in this way, which I denote by f r of n. This is a truncated series. And this is a polynomial where I'm interested. And now the complete Mahler theorem, interpolation theorem, states the following. So you take a function from n to z, and then the following conditions are equivalent. The first one is that f is uniformly continuous for the p-adic metric I just remind you. then the function delta A of f tends uniformly to 0. And the other one is that the lowercase delta A of f also tends to 0, well, for the periodic node, so we take the periodic node. And equivalently, f is the uniform limit of the function fr.
Can you be more specific on which side you put the periodic norm? I mean, you put it on Z.
On both sides. On both sides.
On both sides, but I mean, there are parts where you don't need to put it on both sides. For instance, in 2 or even in 4, you don't need to put it. I mean, or in 3, in 3 you don't need to put it.
I mean. Yes, but that's right. Yeah, but
so at least in 3 you don't need to put it on both. You just need to put it on Z.
Yeah, but okay. I agree. Okay, so that's the end of the introductions. I mean, the commutative setting, and now I want to switch to the non-commutative setting, which is the topic of this lecture. No, sorry, I forgot this. I had 2 examples. So the function r to the n is uniformly continuous if and only if p divides r minus 1 because of this formula. The parity function is uniformly continuous if and only if p equals 2. And the Fibonacci function, the factorial function, which are nice functions, but unfortunately they are not uniformly continuous for whatever p you take. So I think that's is there a question or no? So non-commutative extension. So the natural thing to do first is to look at what are the non-commutative extension of n and z.
Right.
And the natural, sorry, there is some echo somewhere. Can I continue?
Please continue, I think.
Okay.
Please continue, I think.
Well, it's again, someone may have opened his microphone. No? Okay, it seemed to work, thanks. So the natural extension of, for n is just to take the free monoid on some set, which call it an alphabet, A, and the notation is A star. I'm not sure you are all familiar with this. This is it's a standard notation in computer science, but this symbol star is overloaded in mathematics, but I will use it anyway. For Z, the natural non-commutative version is a free group on the set. So the question we have to solve, I would like to solve is, first of all, what are the difference operators for functions from A star to f of v, or more generally to group G? Extend Newton's forward difference formula, extend Newton bijection, we have seen before. And what are the polynomial function, which might be the most mysterious question, and find a metric which extends generalizes D. So let's do this. So just a short reminder to fix notation. The element of the free monoid A star are words. So for instance, if you have this alphabet A, B, C, D, R, you have 2 words, abra and cadabra. The product is the word abracadabra to obtain the concatenation. The empty word is denoted by 1, and it is the identity of this monoid. For the free group, I used reduced word to represent the elements. So there are words on the alphabet A union A inverse. And all you want to have is to avoid to have a chance of the form A minus 1 or A minus 1A. So reduced words include this one, A, B, A minus 1, B minus 1, or A you can use them. And an important fact is that A star embeds into the free group. So the free monoid embeds into the free group. So that's useful because when I consider a function from A star to say B star, I can consider the function from A star into f of d. That's right. So a little bit of combinatorial things that I will use later on, and that's, I don't know if you are aware of that, that's quite a funny notion. Take two words, U and V, which is A1, AN, and you say that V is the subword of U, just means a subsequence, just like this. That's the same definition of the subsequence. So you can find here, A1 up to AN as the subsequence of the full word. And now the binomial coefficient is a number of ways to write V as a subword of V. So let's look at a simple example. If I take this word ABAB, and I consider, this is my word U, I consider the word AB, there are three ways to write it, they are in blue, as a subword of ABAB. So you can see these three possibilities, and therefore the binomial coefficient is 3. And the name comes from the fact that if you take A to the n and A to the n, of course, you get the usual binomial coefficient. By the way, okay, this wasn't, I think this notation was introduced by Heisenberg. So the difference operator, it's quite natural also. It starts with a function from A star to group G. And now for each letter A, you define a difference operator delta A as follows. Delta A f of u is just f of u minus 1 multiplied by f of u. Just the same way as you did in the commutative case. That's very natural. And if you have a word, W, A1, AN, you just iterate this operator to get this. Delta W of F is just delta A1 of delta A2, etc. And you remember I had also some symbol lowercase WF, and they are defined exactly in the same way. Delta W of F is just capital delta W of F taken at the identity, which is empty word, of 1. Okay? If you have questions, just, or if I go too fast, just tell me. So here's a funny example. If you take, what I want to do is to find the iteration of the difference operator for this function, which maps a word x to its inverse in the free group. Very simple question, a simple function. So it defines what you obtain in this. Is it x, A1, AN, this extended commutator, iterated commutator, which is defined just above, x minus 1. That's a kind of a curiosity that you obtain this. I will not detail this computation, but that's not very difficult to see if you take a paper. And the second example is much more, it's a simple function, but it's much more elaborated. So I will spend a few slides on it. So first of all, let me define these functions. This function is defined as follows. You take a word on the alphabet 0, 1, 2, and to this word, you associate the integer n, which represented by this word u in base 3. Now, what is the f of u? F of u is the unique word v of the same length of u, which represent in base 3 the quotient of the division of n by 2. So let's look at an example. I want to compute f of 1, 2, 1, 2. the first thing I'm doing is I just look at F1212 in base 3, this is 50. Now I divide 50 by 2, this is 25. And 25 is 2 to 1 in base 3. And remember, I want to have a word of the same length. So I'm adding this 0 in the front just to get a word of the same length. So the result is 0, 2 to 1. Okay, if you start with 1, 2, 1, 2, 1, this is in base 3, this is 151. You divide by 2, and you get 75, which again is this number in base 3, and the result is this. Okay, so that's this function. Now let's compute the difference operator applied to this function. So let's start with the delta A, where A is the letter. So A is the letter from, you have to be careful because the alphabet is now 0, 1, 2. So when I use delta 1, it's not, or if I use delta 2, it's not, it doesn't mean the iteration twice of delta, but it's just the delta corresponding to the letter. So you don't need to look carefully to this formula, but what you observe is that the delta A of A is always a constant function. It doesn't depend on you. It's a constant function which just depends on the parity of the number represented by B. Okay, so let me verify this on one example. Let's take the letter 1, so delta 1 of f of u. If you remember, this is f of u inverse, f of u1. And if we take u to be the word 1, 2, 1, 2, so we get f of 1, 2, 1, 2 inverse, f of 1, 2, 1, 2, 1. I just added 1. And if you remember the computation we just did, it is this quantity minus 1, an element of the free loop, multiplied by this. So you can cancel this, and you get 0. So this explained, I don't remember, this one, this 0. Okay, so let's keep doing this for delta W. Well, I will not detail this computation now, but the result is that actually delta W of f is also a constant function, always. And this constant function is the identity, except when the W is a word of this form, 1 to the n followed by some letter A. This n can be, actually, I think there's a reason. Yeah, actually, this is also true for n equals 0. So, yes, this was the conclusion is here. The function delta W are constant function. And if W is not of this form, this constant is the identity. So, okay, we will come back to this example later on. Let me proceed to the next one. So now, if you remember the Newton's formula, we wanted to express f in terms of the delta W of f. So let's try. So here we have f of 1 equals delta of 1 of f by definition. Then delta I of f is this. So if I replace f of 1 by delta 1 of f, I get this. So f of a is delta 1 of f, delta I of f, fine. And you keep going. I will maybe not detail this, but if you get delta IB of f, you get this, and you finally get this formula. So this should convince you that it's possible to indeed to express the elements, I mean, the f of u in terms of this element delta. So let's see how it works a little bit more in detail. So here is a more complete computation for the words of length 1, 2, up to 4. And you see it gets fairly complicated. So because it is non-commutative, so we cannot put these elements together, commute this element.
But it has a nice feature that you don't have any inverses, if I understand correctly.
That's right. And you will see there is another nice feature you will see in the next slide, but I totally agree. So, first let me make a little bit of yeah, okay. So in order to obtain this formula in some formal way, I introduce some new notation. So it's getting a little bit more involved. So I consider A star star, which is a free monoid over the alphabet A star. So now the letters are words. And in order to not to confuse things, but maybe to confuse you, this element of A star star is denoted by using an addition. So a typical element will be W1 plus WN, where W1, WN are words. The identity is denoted by 0 because I'm using this additive notation, but be careful, it's not commutative. So typically, so there is a typical element of A star star. So you see that you have 1 plus A plus AB plus A plus 1 is BA. Observe that 1 and 1 here as the empty, the identity of A star, so they're words, and you cannot suppress them. And
so I guess it's a little bit like if you were talking about words and phrases. Huh?
Yes, in a sense, yes. Okay, but the real reason why I'm using this additive notation is that because it's convenient to introduce a monoid right action of A star onto A star star. And this is very simple. You start with an element of A star star, which is a sum of words, each one is descent. U is a word. And now just write this. X, the action is given by this. X dot U is x1U plus x and U. So it's convenient to have this notation now. So for instance, if you have this, 1 plus A plus B plus AB dot C, you get this. So what was the reason to introduce all of this? Is to introduce the so-called non-commutative Magnus transformation. So it's similar to the Magnus transformation you may know, which maps normally A to 1 plus A. But now we are in a non-commutative setting. So mu of 1 is 1. Okay, it goes from A star to A star star. But the induction is given in this way. Mu of WA, where A is a letter, and W is a word, is just mu of A plus mu of W dot A. So let's look at what it looks like. So you see 1 plus A plus 1 plus A times B. So you get this. Mu of ABC is this. And if you want to compute mu of ABC, you start by reproducing this part. And then you multiply this part on the right by D to get this second part over there. Okay? So that's the Magnus transformation. But why? Wait a minute. This is a definition by induction, but would it be possible to find this expression without to have to compute successively mu of A, mu of B, mu of AD, mu of ABC? And actually, there is a trick. I present it as a trick, but of course, it relies on a real mathematical result. But it's funny to look at a trick. Let's suppose I want to compute mu of ABC. So first of all, I order the alphabet in the order of appearance of the letters. So of course, I've chosen this. This is a case where it is a natural order. A is smaller than B, then order is smaller than C. Okay, now the algorithm really starts. You reverse the verb ABC to get CBA. And now you take the subwords. You remember the notion of subword? The notion of, you take the subword of CBA in dictionary order. Yeah, just like a real dictionary. So you get 1, A, B, BA, C, CA, CB, CBA. Okay, Now you take this list and you reverse the words of this list, each of them. So BA becomes AB, CA becomes AC, and so on. CBA becomes ABC. And now you sum this list, 1 plus A plus B plus AB plus C plus AC plus BC plus ABC, and you get A. You have ABC. If you want to compute this, you first compute mu of A, B, C, D, and then you substitute the letters. Okay, so this is the practical trick to compute this.
So from what you said in the last thing, where you put a D and then you substitute A, this means that you create a kind of new alphabet where the things are really distinct.
Absolutely, yes. So in practice, you consider your word, you replace the original word by a word in which all letters are distinct.
Right. Yeah.
You make the computations, then you go back to the order.
Then you go back. Okay, good.
Yeah.
Okay.
So now here is the trick. Look at these two parts of the slide, especially the last one. Here is mu of ABCD, and look at f of ABCD. You see, this is, I guess you can see some similarity, some strong similarity between the two formulas. Especially if you look at the indices here, 1, A, B, AB, and so on. 1, A, B, AB, etc. So there is a strong relationship between mu and this formula giving f in terms of the delta W of f. And we want to make this a little bit formal, but I think this slide explains quite well what is the relationship between the two of them. So the form, now if you want to make it formal, you consider the map delta f, which is from A star to G. Remember, f was a function from A star to G, and the map is defined by delta f of x. X is a word. It maps x onto delta x of f. And this map can be extended in a unique way to a monoid morphism for A star star to G, because A star star is a free monoid over A star, so you can extend, if you know the image of the levers, which are the element of A star, you can define in a unique way a monoid morphism. Well, in practice, this is it. And again, it is convenient with this notation. Delta equal f of x1 plus xn is just the product of these elements, delta x1 of f, etc. And now the forward difference formula I was looking for is simply this thing. F equal delta star f composed with mu. So for instance, you have this. So this is, of course, a little bit abstract, but if you remember the previous slide, it can be complete. Of course, since it is highly non-commutative, it's a bit weird. But nevertheless, let's look back to our two examples. So first of all, I want to look at the first example I consider, the inverse function. It turns out that if you compute delta u of mu for the mu function, it's just the identity. So it means that delta star mu is the identity. So applying this formula we had before, I give you just an example. You get this formula, which I don't know. Actually, I've never seen it in the literature. That's a curiosity about commutators. But of course, you can get as many as you want. Just nothing. The interesting point, of course, is that if you go back to A star equal n, you recover the original forward difference formula, because now this is commutative, so we can group the elements. So let's have a look now at our more complicated example, which was a division by 2 in base 3. So I just remind you that this little formula gives you this coefficient, delta W. I omitted the F, okay? But here they are. And the other coefficient are epsilon. So if you apply the formula to F of 1, 2, 1, 2, you get this. But now you observe that some coefficients are 0. For instance, this one you can cancel because it doesn't start with a 1. Same way as this, you can erase this one, and so on. So if you, this one also, this one, and at the end you get just this. Now you replace using this formula. You get this, okay? And you compute this in the free group, and you get just 0, 2, 2, 1. So F of, so I remind you that 1, 2, 1, 2 in base 3 was 50. And this number in base 3 is 21. So I've just give you a very elaborated proof that of the fact that 50 divided by 25 is 2. Sorry, 50 divided by 2 is 25. Okay, but this, of course, this is a little bit of a joke, but I can tell you that when I managed to verify this was correct, it was a big relief. That's the formula was correct. Okay, let's continue. So, you remember there was this Newton bijection. So we would like to extend the Newton bijection, and the first step to this is to observe, which a non-trivial fact, that if you view mu as a function from A star to the free group over A star, again, it uniquely extends to the group endomorphism of F of A star, takes the free group of A star. And it turns out that this endomorphism is an automorphism. And I put the computation of mu minus 1 as an appendix. So it's not properly in my slides, but if you ask me, I have some slides ready to answer a question on that. Okay, so now Newton's bijection becomes this. It tells you that, just like in the commutative case, the map F to, now this is a family of elements of G where indexed by A star, so this family, this is a bijection. And if you want to make things precise using our previous notation, you get this. F is equal to delta star F composed with mu, and delta W of F is F star of mu inverse of W. I forgot to say that F star was the extension of F to monomorphism from A star star to G. Okay, so it's again a bit abstract, but we got exactly what we wanted. We got the Newton's bijection.
I just have a stupid question, which is that in the case of the Newton bijection, you could get one from the other by putting in signs, -1 to the n. Is there something similar in this case?
Repeat that. You say -1?
Well, what I said is that when you take the Newton bijection, you had two types of formulas. There was one formula in which you had only positive binomial coefficients.
Yes.
And a formula in which you had alternate binomial coefficients.
Oh, yeah, yes.
My question is the following. When you compute mu inverse, can you see something similar?
Absolutely. Absolutely. So we do have negative coefficient. Well, not negative, but you see what I mean. -1. So the computation, probably I will show you the extra, the appendix at the end to explain this in more detail. But this is absolutely true. We do have, contrary to mu, we do have inverse involved in the mu -1. Okay, now you remember, we had this functions, this truncated truncated series, sorry, in the commutative case, back to the commutative case, which is the sum up to R over there. And this is a polynomial function in the commutative case. But the question is that to know whether there is a non-commutative version of this formula. And one of the problems is that what should be a polynomial function? So, you know, here we have a ring, and we use both the addition and multiplication to define a polynomial function. So now we are going from A star to the free group, say, or even to a group, where we just have one operation. So in a non-commutative setting, what should be a polynomial function? And the trick is this. I define a polynomial function as a function f such that the difference operators applied to the power of w where all these different operators are the constant function 1 for almost all words. That is, for all, there is a footnote which says that almost all means all but a finite number. So
I presume that your alphabet A is finite there.
Yes, absolutely. Yeah, yes. We use a finite alphabet. And the degree of f is the smallest d such that w of f is 1 for all words of length larger than d. And there is an equivalent definition. I have to say that this is a theorem. You need to work a little bit to prove that these two versions are equivalent. So a function is a polynomial function if and only if now you just look at the lowercase delta w. And there are 1 for almost all words. And the degree in the same way is the smallest d subject. And if you look back to the commutative case, well, this is true. You know, a function is a polynomial function if and only if you have this property. So in reality, you don't really need the addition with the multiplication. And this is a perfectly correct way to do. Well, of course, you may object, this is not a really polynomial, but it plays this role, at least for this lecture. Let me give you some example. So the interesting case, if you look at a function of degree 1, it's essentially monoid morphism up to it's a translation. It's like an affine function, a translation of a monoid morphism. And if you want to look at a polynomial function of degree, you actually just know of one example, of one simple example. It's this function, which map A1 A1 to A1, A1 A2, A1 A2 A3, and so on. Let me hurry up a little bit. There is a way to generate all polynomial functions. This is this theorem, which tells you that the polynomial function is the smallest set of function containing the constant function and closed under a special operation, which I will define in the next slide, called the sequential product. So it's a surprising result. One operation suffices to generate all polynomials, and exactly that. So let me define this sequential product. It works as follows. You start with a family of function indexed by the alphabet A. From A start with, you take an element G. And the sequential product is the function defined in this way, but don't look at this formula, but just look at this little machine. Consider that the input is the blue part, so A1, AN, and the red part is the output. So the output is G, followed by FA1 of 1, FA2 of A1, FA3 of A1, AN, FAN of A1, AN. As you can see, there are some states. This is an automaton, actually, an infinite one, but which reflects exactly, the A1 reflects this A1 reflects this one, and so on. This A1, A2 reflects this one, and this S3 reflects this input. Anyway, so this is a sequential machine. That's why it's called a sequential product. And this sequential product, as I told you, suffices to generate all polynomials.
So you mean it's a bit like the integral, which generates all polynomials in a way?
Look at them. Thank you for the question.
Well, I have
next slide exactly.
Yeah. Okay.
That's exactly this. So actually, the sequential product is exactly what you say, is that if you know f of 1 and f of a, it's a unique function that such that f of a is the well, if you know the derivative, you can get f with a sequential product. That's exactly so. This integration problem. Okay, so that's what it is. Okay, so now you remember I needed also this truncated series, so that's not very hard. What you just do is you truncate the mu function. So if you start with mu of ABCD, which I reproduce here, you just keep the word of length less than or equal to 2, and here they are, and you get mu2 of ABCD. I don't give you a formal definition, but you see what it is. And now, using our relation giving f in terms of the delta star f, you truncate by just replacing mu by mu r in this formula. Okay? And the theorem, because it's not totally obvious, it turns out that this fr is a polynomial function of degree at most r in our sense. So the conclusion is that this polynomial function fr is exactly the non-commutative version of this truncated series. Okay. Let me see. So I think I'm finished with the combinatorial aspect, but now let me switch to the topological aspect. So what I want to define is a residually p-finite monoids, the properuniformity and the properunity in order. So you probably already know this definition, but just in case, if you start, you have a monoid M, you say that a finite T group separates two elements of M. If you have a monoid morphism from M onto G, such that phi of U is different from phi of U. And a monoid is residually p-finite if every pair of elements of M can be separated by a finite T group. It's a well-known fact that free monoids and free groups are residually p-finite. If you look at finite groups, the residually p-finite ones are just the P groups. So now you have the definition in hand. You can define topology, but also uniformity. So this is a fancy way. I'm not sure all of you know about uniformities, but I didn't prepare a slide to remind you of this. But anyway, next slide we have metrics instead of uniformity. Just to give the definition, the formal definitions is the proper uniformity. This is a coarsest uniformity such that every monoid morphism from M onto a discrete finite P group is uniformly continuous. So you make some uniform structure to obtain this, and this is the so-called proper uniformity. But let's look at metrics, which is simpler. And I will give you a metric for A star and a metric for the field. So for the free group first, you can define the metric as follows. You take two elements of the free group, U and V, and you look at the groups, the P groups which separate U and V, and you take the smallest such P group. So you more precisely, you take the minimum of all n such that a P group of order P to the power n plus 1 separates U and V. And you denote this by RP of UV, and in the usual way, you define the metric in this way. And this turns out to be a metric, actually an ultrametric or non-Archimedean metric. But for the free monoid, I will show you another equivalent way, which is quite interesting also, because it makes use of this binomial coefficient I introduced before. So now you take two words of the free monoid, so, okay, U and D. And now you just consider, you look at the binomial coefficient of U versus X, and you compare the X by where there's the V versus X, mod P. And then you look at the length, this is the length, the minimal length of a word X, which separates U and V in this sense. And it turns out that you define also a metric, and this metric is uniformly equivalent to the previous one on A star. So you have various ways to do this. And here, now let me talk about uniform continuity. So there are three important results I want to define. I want to explain. The first one tells you that a function from A star to G is uniformly continuous if and only if, you remember this element delta W of F, tend to 1 where W tends to infinity, the length of W. Okay, so this is just the same statement as we had in the commutative case with the p-adic norm. That's the first part. The second theorem tells you that every polynomial function is uniformly continuous. And actually, if you can see this is actually a consequence of the following result, that uniformly continuous functions are closed on the sequential product. So a sequential product of uniformly continuous function is uniformly continuous. And since you can get all polynomial functions this way, you get the second thing. So let's look at some example. If you look at the functions mu r, remember they are polynomial actually, not polynomial. They are uniformly continuous, but mu is not. This have to be careful. The function x gives the inverse of x is uniformly continuous, whatever p is. The division by 2 in base 3 is not a polynomial function, because you remember we had these coefficients, so it's not a polynomial. However, it's uniformly continuous for D2. So if p equals 2, it is uniformly continuous. So now we are ready to state the main result, and there's this first version, which is really similar to the version in the commutative case. You consider a function from A star to f of b, where A is finite alphabet. And there's 4 equivalent conditions. F is uniformly continuous for the property metric. The function delta WF tends uniformly to the constant function 1. The lowercase WF tends to 1, where the length of W tends to infinity. And F is the uniform limit of its polynomial function FR, where R tends to infinity. So that's exactly the same. Let me just state the same result in a slightly more general version, where you just replace the free group with any residually p-finite group G. And you get exactly the same statement. So in the remaining 5 minutes, I would like to give you something I omitted from the beginning, which was the original motivations. Before that, I think I have a slide on let's see. I have 2 slides. Yeah, I have a slide on some interpolation results. This was actually in Mahler's original paper. He asked whether it's possible to extend a function from n to z into a continuous function from the periodic numbers to itself. And here we replace the periodic number Zp by the free tropy group FPOA. So what it is, you start with a free group and you make the completion. You know, this is a metric space. You just take the completion. There are other ways to define it, but this is a simple way. And this theorem tells you that a function from A star to the extent to continuous function from the free, the pro-T group on A to the pro-P group on B, if and only if this coefficient tends, usual condition, the coefficient tends to 1 when W tends to 1. And in this case, the extension is 0. So let me finish as I promised by giving you the original motivation. So you maybe observe that I'm in the department of theoretical computer science. So it came from formal language theory. What is a language? It's just a subset of A star. We have a special name for it. The main definition is this one. A language is recognized by a monoid M, so a subset of A, if there is a monoid morphism from A star to M, and a subset P of M, such that you have this. L is the inverse image of P. This is a very, very simple definition. And you say that the language is regular or recognizable if it is recognized by some finite quantity. So for those of you who know about automata theory, yes, they are exactly the same, but except that this definition, in my opinion, it's a mathematical definition of a regular set, which is much better than the one with automata. But let me close this parenthesis. And now let's call a language to be P-recognizable if it's recognized by not by any monoid, but by a finite P group. So this language, these P-recognizable languages, were studied by 2 people you know, that's at least the first one, Heidenberg and Schützenberger. And they prove the following nice results to tell you that basically these P-recognizable languages are obtained as finite Boolean combinations, which means finite intersection and union, and complement is not needed actually, of these languages, where again you have this binomial coefficient here. So you take a set of words such that Ux is congruent to R mod P for some fixed word X. You get a language, and it's recognized by a P. That's not very difficult to show, but it's more difficult to prove that you get all P-recognizable languages in this way. So what was the problem? It was a so-called synthesis problem. You say that a function is regularity preserving if for each regular language, the inverse of image of L is regular. And in the same way, a function is P-preserving if for each P-recognizable language, the language F-1 of L is P-recognizable. And the synthesis problem is to describe the set of all regularity preserving functions, or the set of all P-preserving functions in this case. And so the first problem is still open. But the second one is the solution is given by this. The set of all P-preserving function is the smallest set of functions containing the constant function, which is closed under taking sequential projects, and uniform limits. So we have a complete description of this family. You have to observe that this class contains some non-recursively enumerable functions. So you can get, because of the uniform limits, you can get difficult stuff. I think this is, no, there is still an example. The example is this one. If you take this function again with binary, this time with binary numbers, let me explain what you do. You want to compute f of 26. You write 26 in binary, okay? And I think I made a mistake here. I think there is a typo here. And you replace the most right, oh no, that's correct. You replace the most right mode bit 1 by 0. So this is, you replace this 1 by 0. And now you get the result, this is 24. It turns out that this function is uniformly continuous for D2, it's 2 preserving, but it is not regularity preserving. So if you compute this, you obtain a language which is not regular. Okay, sorry for this, but this time, this is the end. And I would like to thank you for your attention.
Thank you, Jean-Eric. Thanks. Are there any questions or comments?
So maybe I want to show. Yes, it's just to answer Alain Cohen's question, just without.
Yes, yeah, it's exactly what I had in mind. That you had to put minus signs where there were plus signs before. Yes, yeah, yeah, that was it. Yeah.
Well, it's not exactly the same in the same order.
No, not in the same order. But what I meant was that the formula is very similar except for minus signs. Yes.
Yes.
Okay, that's very interesting. Yeah, no, I appreciate. I mean, I think it's great stuff, really. I mean, for lots of different reasons. I mean, yeah. I had one question which is not really related to the non-commutative case, because when you were showing the factorial and you were saying that it was not convergent and so on, this suggests not to take the factorial, but to take the function which is related by the Newton bijection to the factorial. Because the factorial itself, of course, is divisible by any power of prime. So after a while, so.
Yes.
Okay, any other comments or questions? Yeah, it looks like there are no other comments or questions. Okay, so let's thank Jean-Eric for a beautiful talk. Thank you so much, Jean.